Good afternoon, everyone. My name is Xiaoyuan. Today I'm going to present our paper named Towards Understanding Toolchain Bugs in the LLVM Compiler Infrastructure. This is a joint empirical study from Wuhan University, Nanjing University, and Swinburne University. First of all, I would like to briefly introduce our motivation. It is known that LLVM was derived from a research project. On one hand, it is now a very popular and widely adopted compiler infrastructure. On the other hand, it is not a piece of standalone software. Instead, it is a collection of modular and reusable compiler and toolchain technologies. As a consequence, the tools under LLVM usually work interactively with each other in order to finish a particular task. Due to the popularity of LLVM, its quality becomes very important because bugs in LLVM produce an unexpected impact on its large user community. Therefore, it is necessary to have a deep understanding on the LLVM bugs. But it should be noted that the frequent interactions among LLVM tools bring a common and important type of bugs, namely toolchain bugs. These bugs are not limited to one tool, but are relevant to multiple LLVM tools. For example, this is a real-life bug in LLVM. This bug was observed when running compiler RT, but was finally ascribed to Qiang. On one hand, these bugs involve multiple tools, whose detection and fixing can be generally more complicated. On the other hand, these bugs usually contain richer information and hence should never be ignored. However, to the best of our knowledge, there's no prior work that specifically concentrated on these LLVM toolchain bugs. Therefore, in this paper, we will provide the first comprehensive empirical study to deeply understand toolchain bugs in LLVM by mining important facts from real-life data. We aim to reveal insights that can be utilized in future bug detection and fixing processes. Before we formally introduce our experiment and findings, let's talk about some preliminary concepts in this study. First is the toolchain. A toolchain is a set of tightly coupled programs which can collaboratively complete a complex task. In recent years, many famous toolchains are provided for a broad range of applications. Nowadays, LLVM has become a mature and reliable compiler toolchain. It contains 11 primary tools. As mentioned above, these tools usually cooperate with each other. This figure illustrates the interactions among different LLVM tools. These interactions bring a specific type of program bugs, that is, toolchain bugs. In this paper, we conduct the first comprehensive empirical study to deeply understand these toolchain bugs in LLVM. Specifically, we are interested to answer the following research questions. Our first RQ is to answer how prevalent the toolchain bugs are in LLVM. It aims to reveal the overall amount and distribution of toolchain bugs such that we can understand the potential impact of these bugs. Our second RQ aims to investigate whether LLVM toolchain bugs have any typical patterns. Specifically, we will first reveal the combinations of tools that are more frequently getting involved in program failures. Secondly, we will mine these typical reasons of interactions among the involved tools. Finally, we investigate the typical failure behaviors reported by these toolchain bugs. By revealing this evidence, we hope to highlight those bug-sensitive interactions and symptoms such that people can pay more attention to them during development, testing, and debugging. Apart from inspecting the bugs, we are also interested in their corresponding debugging process. Thus, we investigate typical manners for fixing these toolchain bugs in RQ3. Generally speaking, it is relatively complicated and difficult to debug a toolchain bug. The recorded failures of toolchain bugs could be revealed in one tool, but the real root causes may be in another one or due to the interactions among different tools. So in this RQ, we will answer what are the typical root causes of these bugs, how are the involved tools modified in order to fix a toolchain bug, and how are the non-involved tools modified in order to fix a toolchain bug. We collect bug report data from LLVM Bugzilla. We identify a bug as a toolchain bug if more than one LLVM tool names appear in this bug report. The collection procedure is done via the search engine by using this query. Overall, we have found 1,723 toolchain bugs. We also export all commits from LLVM SVN repository. We rebuild the linkages between the bug reports and their corresponding commits by using these rules. First, we look for bug reports that explicitly provide the feature of fix by commits. Secondly, we refer to the fixing commit ID mentioned by the bug reports in their comments. Finally, we search for the issue ID mentioned by commit logs. Overall, we have linked 654 bugs with their fixing commits. Next, let's formally discuss our findings. For RQ1, this table demonstrates the number and distributions of toolchain bugs. It can be found that the percentages of toolchain bugs are as high as about 14 and 19% in Poly and compiler RT respectively, while are relatively small in the rest of the tools. However, by inspecting the absolute number in Qiang and core libraries, we can find that they're actually not small, which are almost 1,500 respectively. For RQ2.1, we first analyzed the distribution of the numbers of tools involved in toolchain bug reports, which is shown in this figure. We further inspect the frequency of each distinct combination. This figure demonstrates the top 10 combinations of tools. We found that Qiang appears in the top 1, 2, 3, and 5 combinations, which indicates it is very important. Besides, the core libraries also plays a very vital role, which appears in the top 1, 4, 6, 7, and 9 combinations. As a consequence, the result that Qiang plus core libraries becomes the most frequent combination. This is actually in line with our expectation. Next, in RQ2.2, by deeply mining the collected data, we have found 6 frequent and representative reasons for tool interactions. The first one is collaboration between Qiang and the core library. The second one is invocation among libraries of different tools. The third one is tools interaction while setting compiling options. For example, options involving other tools are set in Qiang commands that are generally first invoked as the compilation entry, and hence the observed failures are usually attributed to Qiang. The fourth one is setting optimization options using Qiang during compilation. This mainly includes interactions between Qiang and core libraries and Poly. Next is building multiple tools in the process of the toolchain build. Sometimes tools in the LLVM toolchain are built and used together by some automated tools such as the CMake to form a toolchain. In this case, there exist dependencies and collaboration among these tools, thus they may appear together in one bug report. The last one is checking or tracing the operation of tools using compiler RT. Compiler RT provides runtime libraries for dynamic testing with which running programs, especially the invoked tools, can be monitored and traced, and exceptions can be found accordingly. With the help of compiler RT, other tools can be found to have problems. Among all the investigated bugs, we have found these categories account for these portions. Among the collected bugs, we have found 4 typical symptoms that are compilation failure, optimization exception, invocation error with options, and tool build failures. Through the above findings in RQ2, we have found intrinsic relations between the interactions and the failure symptoms. That is, some interaction manners tend to have specific symptoms. For example, the second typical interaction manner usually implies the first typical symptoms. Next, let's discuss about the findings in debugging process. By carefully reading the bug reports and their corresponding fixing commits, we summarize 6 typical root causes of these toolchain bugs. The first one is instruction issue. During the instruction generation, some problems such as wrong instructions, instruction out of order, and instruction image errors would lead to toolchain bugs. The second one is memory issue, which could be memory space allocation issues, address redirection issues, and variable alignment issues. The third one is linkage issue, which mainly include missing required functions or files, linking to useless or problematic files, or linking to inconsistent versions. The fourth one is environment issue. The LLVM toolchain is a cross-platform development toolchain. However, when a tool is designed without considering the differences between different platforms, environment issues may occur. The next one is error checking issue. In the LLVM toolchain, each tool has an error checking and handling mechanism. However, as the code evolves and updates, sometimes the test insertion becomes invalid, which may affect the running and building of the entire project. The final one is configuration issue. During the build of the LLVM toolchain, the process should be configured in file CMake list. The whole build process would involve one or more tools with complicated relationships so that the configuration files are actually error-prone and sometimes lead to failures in the project build. Among all the recovered linkages, we have found the above causes account for these percentages. While in the investigation of how the involved tools are modified, we first give the overview distribution of the number of modified tools in the toolchain bugs, which are shown in this figure. Next, we compare the list of involved tools in the toolchain bug report and the list of modified tools in its corresponding fixing commit to check their consistency. This table presents the percentages of bugs where all the involved tools are modified. Only part of the involved tools are modified, as well as none of the involved tools are modified. It can be found that in most cases, only part of the involved tools are modified, and there are also cases where the modified tools are never mentioned in the bug reports. As a reminder, we also investigate percentages of cases where the product field is modified. Generally speaking, the field product in the bug report is used as the representative affiliation of the bug and is usually regarded as the approximate location of the bug. But when we found that the affiliation of the bug shows obvious inconsistencies with the actual modified tools, that is, tools in the field are not always modified in the fixing commit. This means that the affiliation of the bug do not necessarily imply the fault locations. Here, let us use the bugs whose fixing commit modified only one tool to demonstrate this inconsistency. Overall, we have found 117 bugs show this inconsistency, which account for almost 20%. For example, we found 84 bugs who were categorized into Qiang, but were actually fixed by modifying core library. Through the data in RQ 3.2, we can observe that some fixing commit modified tools that are even not involved in the bug reports. Thus, in the final RQ, we investigate how the non-involved tools are modified. This table presents the percentages of 1 and 2 non-involved tools being modified. We have found 60 out of 654 bugs having at least one non-involved tool being modified. We further carefully read the bug reports and commit logs and summarized 2 typical reasons. The first one is very straightforward, that is, the non-involved tools are actually problematic ones. But there are also cases where the non-involved tools are modified simply because of the workaround fixing. Finally, we would like to discuss the insights and conclude this work. Our summarizations on typical interactions, failure symptoms, and root causes can serve as useful experience for fault detection, location, and reasoning. To effectively detect toolchain bugs, we can adopt variable or mixed strengthened combinatorial testing by referring to the observed bug sensitivity of different combinations and interactions. To locate the root causes of toolchain bugs, we can refer to the relations between the failure symptoms and the commonly seen root causes. As a reminder, it is also necessary to consider non-involved tools in the report. To summarize, this paper makes the following contributions. It provides the first empirical study on LLVM toolchain bugs. It reveals 6 typical patterns of toolchain bugs and 4 common symptoms. It identifies 6 common root causes and summarizes typical debugging manners. Finally, it provides insights for future testing and debugging this type of bugs. So that's all for the presentation. We are really sorry that we are not able to give a live presentation due to the time difference between China and the US. It is now midnight in China. We have already released our data on this given link, and we also welcome any questions. So if you are willing to discuss, please contact me or the corresponding author. And thank you very much.